again, sorry I always start a bit late. Just I have, only so much time to jump between one class and another. So I had a pretty amazing night last night. And it's not like because I, went to a party or anything. No, it was because I got nerdy and spent a couple of hours on my laptop working on your next homework, which you may be able to figure out the topic of which if you look at the board, which is, now you may be wondering what the heck stacks and mazes have to do with each other, and we'll get into that, but first the most important announcement, which is about the exam. Now, as many of you mechanically emailed me, you do not have an exam next week because, again, my promise is I give you a practice exam the week before. Since you had no practice exam the week before, I feel it would be completely unfair. Well, not completely unfair, but it would be somewhat unfair if I gave you an exam to work, this week. Right? That makes sense? So you guys don't have an exam this week. The consequence of this, well, not really a consequence. The consequence makes it sound bad, but the consequence of this is that there will be a question or two about stacks on there. There will be like one 10-point problem on basically using a stack to solve a problem, which, as we've seen in class, that's not too hard to do, right? Solving a problem with stacks. If I tell you it's a stack problem, it's because of the way stacks work. It's pretty easy to figure out. Oh, I need to push and pop stuff. I just got to figure out what I'm pushing on, what I'm popping off, and when, right? That's literally all you have to think about for stack problems. Okay, so let me show you what I did last night because this I don't basically every semester my students act as guinea pigs in one way or another, because it's just there's always the goal that I can always teach better, do something better. So I always try to come up with something new and interesting. So let's go ahead and I think I want to duplicate these displays rather than extending them. We still recording fine? We should be still. All right, so let's go ahead and hopefully, okay, great. So here's a private repo. This teaching repo is my private repo, which is why it's where I keep all my exams and stuff. And it's not on GitHub. So here is what I did last night. So I worked on writing something with a maze, and not just an ASCII, but actually, doing this. So full disclosure, I once upon a time knew how to do graphics. Probably like my freshman year and sophomore year, I learned plenty about how to do graphics in Java. I've promptly forgotten all those in the year since my freshman and sophomore year, and I wasn't a particularly good student in my bachelor and sophomore years. Nevertheless, I wrote this. Took me about 4 hours to figure out how the graphics work, which you will not have to do. The graphics library is this. This is what you are going to get as your problem. Okay, so basically, and I'll go through it in more detail once I censor out the problem I want you to solve, right? But this is actually a maze. This is a maze generated by one of the stupidest, simplest maze generation algorithms there are. Now there are stupider maze generation algorithms. So let's go over the stupidest maze generation algorithm. The stupidest maze generating algorithm is we start out with basically a bunch of places, okay, a bunch of cells. And we perform what's called a drunkard's walk. There's a more formal name for it, but everybody remembers it as the drunkard's walk, which is that basically imagine you are some drunk guy, okay, which means you are stumbling around in who knows what direction, okay? So these are a bunch of cells, and basically if I haven't visited this cell yet, and I stumble into this cell, I remove the wall between this cell and this cell. Once I've visited a cell, I don't remove the walls anymore. But the idea here is that basically you just randomly stumble around creating a maze, okay? So hence it leads to a lot of winding corridors. That's not what I did here. What I did here, I don't know if it has a formal name for it, but it's essentially the northwest removal algorithm. What I did is I removed all the east-west walls on the first row, and I removed all the north-south walls on the first column. Okay. Then for every other cell, I randomly chose, am I going to either remove the wall to the west or the wall to the north, right? So this one, you can see he chose to remove the west wall. This guy chose to remove his north. He removed his north. He removed his north. All these guys removed their north walls. Let's see. This guy finally chose to remove his west wall, right? So we just simply do that for each cell. They just simply choose to remove their north wall or the west wall. And in the end, we get ourselves a maze. And the idea here is that we start here and try to find a path to here. That makes sense? So we start from here, go to here. Okay? And the code actually isn't too bad to do that. So let's see. So maze panel, let's see. So dupe. So solve maze is what you'll do. I'll give you some of that, but I'm going to minimize that. But here's the code to do that. I simply have a row of what I call cells, which are basically these individual pieces of the grid. You can imagine this is a n by n grid, where n is the number of cells I have, right? And so for each cell in there, if you're the topmost square, I'm going to skip you, right? Because I don't want you. The top left, I want to skip you. Else, if you're in the very first row, remove your west wall or your east wall. If you're in the first column, remove your north-south wall. Otherwise, flip a coin. Okay, flip a coin. Right? Math.random produces a double that's between 0 and between 0 and 1, non-inclusive of 1. So if it's less than 0.5, then we're going to go north. Otherwise, we're going to go south. So if we're going to go north, we remove my northern wall and the guy above me his southern wall. That makes sense? And otherwise, I'm removing my west wall and his east wall. Okay, that's not something you have to worry about. And then repaint, I was just being cautious here. I don't think I actually have to need to repaint. And that's pretty much all there was to it. A cell is pretty simple. It had 4 variables for the walls. And I'll go into more detail when I get this out to you once you see what the homework is. So int row and int column, just to keep track of what row and column I personally am in the array, because that way it makes it easier. And then paint component. Basically, I set the color here. Basically, I'm saying I'm setting the color of my pen to black. Okay. And then if I have a north wall, I draw a north wall. If I have a south wall, I'm drawing a south wall. If I have an east wall, I'm drawing an east wall. If I have a west wall, I'm drawing a west wall with the draw line. And what color is it going to be? Well, I said I'm setting my colors pen to black. So, for instance, if I do this, oh, I had it twice over here. So you can see I have some redundant code. So if I change it to red over here, as you can see, it should change it to a red maze, as you can see, where I draw my... So graphics aren't nearly that hard in Java, as you are led to believe, but it is a lot to take in all at once. Okay, so the constructor simply says, just set the color of my, pass color.white to this one, which honestly, these are deprecated, so I can probably remove them. Boom. Boom. Okay. And that shouldn't cause any problems. Okay, so the constructor is the cell int row. Set the background of my cell to white, right? This dot set background to white. Now, the reason I can do that is because a cell is what we call a J panel. And I'll go into this when I do put up a companion video for this lab, because it does deserve a companion video to go along with it. The idea here is that we set the color of the background to white and say, hey, you're looking at row and column, and you've got all your walls because nobody's torn them down yet. And then that's fairly straightforward as to what it does. Now, your assignment. So I'm giving you all this. Your assignment is to finish the last part of what I did last night, which is to solve the maze, and that took very little time for me to write. It took me about a half an hour, between a half an hour and an hour, including the stupid errors I made. And that does this, which is that it finds a route from the top left to the bottom right. So the green is the correct path, and the gray is the incorrect path. Now, normally I would talk about this during recursion, but recursion uses a stack anyway. It just implicitly does so. So it's actually the perfect time to introduce stacks. This is an assignment I've wanted to give out forever. So your assignment this week, or that I'll be giving you this lab, is to create a maze-solving algorithm called the recursive backtracking algorithm. Now, generally, it's my maze talk is much better received when I'm talking in like early October when hedge mazes start coming up, and so people like to know how they can get out of any maze. which is actually pretty easy. But here, what we've done is just a fairly straightforward algorithm, which I'll go into without giving you the code for it, because the code is actually, it's just verbose. It's not so hard. Once you figure out how to check north corridors, you just flip it around and for east, south, west, and for east, south, and west. But the idea here is that this algorithm simply says, okay, look at what directions I can go. Can I go north, south, east, west? I'm going to go choose, so my directions where I'm checking north and south and west and east. So can't go north, can't go, but he can go south. And he makes the same, and right over here we make the same choice and go continuously down. Now this grayed out area is stuff that he visited and had to backtrack through. So that's a lot to take in. So how does a stack, so why am I bringing this up now? Well, the idea here is that the stack is the perfect data structure for solving this. Okay, but first let's talk about just how to solve a maze in general. Okay, imagine that this classroom is a maze. Okay, that this classroom is a maze, and these are corridors. That these are basically walls. Okay, over here that are decimal walls, and that basically this is the entrance and this is the exit. How can I write an algorithm that will guarantee that I get to the exit? Right? And it doesn't matter what the configuration of the desks are. Right? Now, the most basic algorithm for solving mazes is called the right-hand rule, which is different than the actual right-hand rule in math, which is that I slap my right hand onto the right wall as I enter and don't let go, which means that basically I hold on and then basically I trace a route. Okay? And I hold onto the wall, and then I would simply hold onto the desk as I go along, and then I'd simply do that in between each of the corners of the desk. But along the back, and you can see that would allow me to get along the back wall and to that exit. Now this works on a lot of different mazes, especially when the entrance and the exit, specifically when the entrance and the exit share a wall. They basically notice that they're both on, the entrance and the exit are on the outer wall. So long as there's a path leading from the entrance, the wall, the entrance, the wall, the exit, this will work. Okay? This is the most basic maze generation algorithm, and it will work for basically anything that's not a labyrinth, meaning, not a Greek labyrinth, where basically your goal is maybe in the center of the maze without any attaching walls. So, but for other mazes, we need something a bit more bulletproof, which is what we call recursive backtracking. Now, this will be the topic of a lot of discussion. We're going to bring it, we'll have a hiatus on this when we go into queues, and then we're going to go into this when we talk about recursion again. But recursive backtracking is one of the most powerful tools that we have available. Now, we aren't actually going to go into recursion because you've got an exam, and why should I, hit you with something as complicated recursion as that before going into the exam? So instead, what we're going to use is a stack. Right? Now, let's review what are the operations we can do with the stack? Yes? Pop? Push? Peek? Pop, push, peek, and the last one, of course, is empty. Right? So we can put something onto the stack, and then we can pop something off the stack. So let's go ahead and look on the Wikipedia page for the maze generation algorithm. It turns out that maze generation algorithms and maze solving algorithms are pretty close. You can basically use the same ones. Media, and I'm just more doing this to prove a point. Maze solving algorithm. Okay. Maze generation algorithm. So here is the maze generation algorithm. There's a bunch of stuff with graph theory and stuff, but recursive backtracker. The depth first search algorithm, which just simply means we go deep into a corridor as we can before we back up, as opposed to checking basically all the corridors equally, like going one step down one corridor, then one step down another, then one step down another, then two steps down each, then 3 steps down each. That's a way to get nowhere fast. But it is a way to work on it. Okay? Mark the initial cell as the current cell and mark it as visited. While there are still cells to visit, or in our case where we're trying to solve it, while we haven't reached the end of the maze. If you have neighbors who haven't been visited yet, then randomly choose one of your unvisited neighbors, or methodically choose them in my case. Push that cell into the stack. So there's that term, push the cell into the stack. Remove the wall between, so this is the generator maze. Remove the wall between your cell and the chosen cell, and make the chosen cell the current cell and mark it as visited. So if you have cells to visit, you go down one of the cells. And you keep doing that until you reach a point where you can't visit any cells anymore. Else, if your stack is not if you can't go anywhere from where you are, right, you're at a dead end or something, okay, pop a cell from the stack, and now that's your current cell. So the idea here is that the stack allows you to recursively backtrack. So let's see how this works in practice, right? Here is a hexagonal maze. So we started here. He's drawing a maze right now, and what he's doing is that basically he's just choosing random directions to go until he reaches a dead end. So let's make sure that, okay, that's weird. There we go. So the idea here is that he's just going, and then eventually he's going to get into a dead end like he just did there. So once he hit a dead end, right, he was keeping a stack of like saying, okay, I'm at this location, then this and push that into the stack. I'm at this location, so I push it out to the stack. So he does that for every location he visits, okay? And then once he gets this spell, he's like, okay, I'm stuck. How do I know where to go? Well, if I pop the top of my current location off the stack and now look at the top of my stack, that tells me that I should be here. And so I can keep backing up. Imagine that you have, so the way to imagine this is that you're using the stack here and the visited. So is that we have two tools here. The first tool is a bag of chalk, okay, and like speed chalk or something. Maybe it's like some kind of chalk paint that you can just splash on the floor to tell that you're there, right? The idea here is that I've got some chalk and I can mark as squares whether I've been there or not. So this is useful to make sure you don't end up in the loop, right? Marking corridors to make sure you don't end up in the loop. Otherwise, you're going to possibly meander along this maze forever, right? You got to know whether or not you've been to a place or not in a maze, okay? Because if you've been somewhere, there's no point in going back to that place unless you're backing up. Now, the other thing you're keeping with you is a ball of twine, a ball of string, okay? And this represents our stack. And the idea here is that we take this ball of string and nail it to the entrance in the maze on one end, and then we unwind it as we go through the maze, okay? And then if we get to a dead end, well, we can just roll the string back up until we get to a point where we're no longer at a dead end. Does that make sense? So the stack in this sense is your string. Does that metaphor make sense to everybody? Okay. Doesn't like me pausing. Okay, so here it's going through. See, it's just backtracking a lot to find new places to go. And so now it will fully generate the maze. It finally hits those. So basically, because it's a maze, it's trying to make sure it hits everything. So it's going to go back and hit that spot. And so now we've got a maze that was solved with recursive backtracking, okay, or that was created with recursive backtracking. But let's go ahead and look at a maze solving algorithm. Rosetta Code. So Rosetta Code is a site where basically, if you want examples of some piece of code like Hello World, you can go here and look at it. Here they've got an animated version and an unanimated version. So they did this one in ASCII. Basically, the idea here is that it winds down the maze, and then it selects, okay, can I go down? Well, I'm going to try going north first. Oh, that's a dead end. So I back up. The idea here, again, is that, let's see if they use Control-F stack, right? The 18 matches on this web page, right? In the JavaScript version. So the idea here is that by using a stack, we can go through this maze and basically figure out where we need to go. So this is a recursive algorithm. It doesn't use a stack, but mine uses a stack. So going back to this, the way I worked was I simply asked, okay, is there a north? Can I go north? No. Can I go south? Yes, I can. Can I go? So I push this onto the stack. So I push this location onto the stack. Can I go south? Yes, I can. Push this onto the stack. So I keep doing that because I have a bias to go south. Okay? So I go south this way, keep going south until I hit this dead end over here. Right? Everybody see this is a dead end over here? So now I'm like stuck. Where do I go? Well, I need to back up. So this entire thing was green. Okay? But the issue is that basically now I'm using green to mark my path to there. So when I back up, I colored this gray so that I know I visited there, right? White I'm using the color of the cell to figure out whether I've been visited. So the colors aren't just for my benefit; they're for my algorithm's benefit too. So here, if I go down, color this green. Oh, I back up, I color this gray to know that I've been there. Okay, so now I'm here. I can choose either to go south. Nope, that's not going to work because I've been there before. That's been visited. Let's take a look at that algorithm, by the way. By the way, I have a function here, right? Visited, okay? Public Boolean visited, int row and column. I grab the cell at row and column. I get the background color, right? C.getBackground, color status. If the status of the color, if the color is equal to white or red, I used red for my ending point, then I haven't been there yet. Otherwise, I've returned true because I totally have been there because it's some color I've used. Make sense to everybody? So I go down, so I'm here now, and I go, oh, okay, I can't go this way, but I can go this way, so I color this green now. And then I color this green. Oh, wait, I'm at a dead end again. So I pop off the stack to get my current location. I'm at a dead end, so I pop off the stack, pop off the stack, pop off the stack, pop off the stack. Oh, I'm here. So let's go to the right again. And then I just continue in the same way. Pop off, pop off. So it just basically figures out that it can't go in these things, and so it backs up. So everybody see how basically what I'm doing is what is the algorithm here? So let's go ahead and write it on the board, what this algorithm is. Okay, so imagine I have a stack. Basically, I've got my current cell. So pseudocode here. If my current square is equal to an n square. So if the current square is equal to the n square, which you'll need to use, this is pseudocode, so you'll probably have to use dot equals and stuff. Then I'm done, right? So done equals true. Okay. Else, if can go north, right? Otherwise, if I can go north, and the way I can do that is actually ask, does current dot north wall, right? Because does current not have a north wall, right? So not current dot north wall, right? And visited current. So how do I go north? So if not visited, current dot row, right, -1, current dot col. Make sense there? Current dot row -1, that's one row above me, right? So if I don't have a north wall and I have not visited the current row -1 and the current column, so one square above me. So if I haven't visited that yet, I want to go there, right? Which is that I will do, and how do I go there? Well, I'll say that basically that I'll set this color equal to green. So let's go ahead and say cell next is equal to maze row -1 call, right? So I get that next location that I want to go to. Okay, so next maze next dot set background to color dot green. It's all caps actually for the green. GREEN. And then stack dot push next onto the stack, right? So I can keep track of it. Then I repeat this for south, east, and west. I just change the variables up. So So once I figure out how to do north, it's pretty easy how to figure out how to do south, east, and west. I just change the pluses, the minus to a plus in some cases, and then I also subtract right from the column. So the other condition is else. What if I need to back up? Set current. Current is equal to, so first we set current dot set background to gray, because if we can't go north, south, east, or west, we're at a dead end, right? So otherwise we set the background of current equal to color dot gray, and then current is equal to, I don't know if this is how I did it in my code, but this should make sense to you. Current is equal to is equal to stack dot pop. In other words, we get the last location that we put onto our stack, right? When we visit a place, we push it. And if we back up, we have to pop. Does that make sense to everybody? So I'll give you basically a lot of this code. I'm also going to give you my maze generation code. And we'll see what we can do with this. This is a new assignment. Yeah, you're working with graphics and you have no idea how to work with graphics. I didn't know how to work with graphics either, but the idea here is that you're not doing anything more complicated than setting the colors up for anything, right? I'll give you these 3 files, and they're all pretty sparse, actually. So the files I'll give you are this maze file, which I'll appropriately name. And don't worry, the camera was able to catch it. So, and I will put this up in a video as well for you guys. So here I can set the size of the maze, by the way, to like whatever I want. Okay, and then set the size of the window. This just simply says that when I hit the exit when I close the window, terminate the program, pack it all up for the user, and make sure, the user can actually see the window. That's all this file says. So create a new maze grid panel, which is the actual, maze itself. Put it into this frame, pack it up for the user, make sure that it closes when I tell it to close, and make sure that they can see it. Right? And here I just changed the variable so it's a 50 by 50 maze now. Can do this. Let's see. What if can I make it like this? 500 by 500. Doesn't like that too. Oh, wait, no, it's just taking much longer to generate, I'm sure. Let's go ahead. So 100 to 100. Let's go ahead and see. There's a 100 by 100 maze. So this thing does pretty well. So the maze grid panel, I'm going to give you all this except for including the let's see. So, oops. What I'm going to give you is all this stuff, all this code that you currently see. Solving the maze is your main assignment, which I think took me 28 through 75. And I was a lot more verbose than I needed to be, and I have a lot of white space in there too. Then the other one is generate DFS maze. So you can also write your own generation algorithm for extra credit using mine as a guide. Okay. And then you've got the cell, which we've went through. So stacks are actually really powerful if you can use them to do stuff like solving mazes. Okay. So hopefully I didn't scare you or bore you too much. But this is what I whipped together last night. I was fairly proud of it. So. Even though it's not really super exciting as far as graphics are concerned. So let's go ahead and resume where we were on data structures. So, all right, we were going through the slides for stacks, and we had left off at the point where we wanted to talk about infix notation, right? Did anybody bother looking that up over the weekend? About infix versus postfix notation and how computers do math? Nope. That's fine. So the idea here to resume is basically that we don't like computer scientists love and hate those this is the correct way to do PEMDAS as much as anybody else. Right, because there's all weird sort of rules when it comes to PEMDAS, and when there's actually like when you've got something like this, like when you've got something like 3x over 2 plus 1, right? You know, what is the implications of what goes on? You know, where are the parentheses in this? Does using division like this have parentheses? What about, are the rules different when you use this symbol or when you use this symbol? Because believe it or not, there are some math texts that say, yes, it's different when you use this. So, so we hate those notations. So instead, what we're going to do for our computers, because we don't want them to get in Facebook arguments, is that we're going to do something called postfix notation. And the idea here is that we're going to create a completely unambiguous mathematical notation. Now, this notation is also called reverse Polish notation because it's the reverse of Polish notation, which is prefix notation. So prefix notation, by the way, is another unambiguous one, which simply looks like this. Star 3, 2 means I want to use the star operation on 3 and 2. And you might recognize this if I do it like this. It's a function call. So prefix notation uses this function call kind of stuff. So that would give you 6. Okay. Postfix notation is useful because it's pretty nice for a stack to do, and it's not too hard for a human to follow once you learn the rules. So the idea here is that we are going to create a stack, okay, which will be visualized by this tube that I'll draw up on the board, but you can't see because I've got slides up. So that's okay. I'll change the camera in a bit. And the idea here is that what we do is that we will push 4 into, if for expressions in postfix notation, we will push a 4 into this. The way we evaluate this is that we push the 4, we push a 7. In fact, any number we see, we just push it into the stack. So here I'll switch to the camera and show you. So here we've got 4, 2, star. So what I do here is I push 4 onto the stack and I push 2 onto the stack. And then once I hit the star, what do? I pop off twice. These are all binary operators, so I'm going to pop off twice. Okay? This will let the first thing I pop off be the second operator, and the first thing I pop off be the first operator. Sorry. So 4 and 2. So now I just do this operation on 4 and 2. So I multiply them by 8 and push these two guys and push the result back onto the stack. Okay? So now let's do something a bit more interesting. So let's go ahead and do 4, 7 times 1 plus. Okay? So now 4 goes on the stack. 7 goes on the stack. Times. So we take out 7 and 4 and multiply them together. So 4 times 7 is 28. And we push 28 back onto the stack. Okay? Now we push 1 on top of the stack. And then we get to a plus sign. That means we pop off the 1, we pop off the 28, we add them together, we get 29, and we push the result back onto the stack. The last one, to get your answer, just peek at the stack. And you're done. So these are completely unambiguous operations here. So over here, we've got 4, 7 times to get 28, 4, 7, 2. So here we pop off 2 and 7, right, to get 9. And then we multiply 9 by 4. Okay. Here, again, we get 4, 7 times. So we put 28 on top of the stack. We put 28 on the bottom of the stack. Then we add 20 on top. And now the minus. Now remember, the first thing we pop off is the second operand, right? So 20 goes on the left side of the minus, and 4 and 7 go on the front side, right? The front side is the older stuff that's in the stack. So even though this looks complicated, right? In some ways, it's no more complicated than these awful parentheses, right? Nested parentheses. And the idea here is that we don't actually have to go through nested parentheses and worry about PEMDAS. We can just simply do 3, 4, 7, multiply to get 28. Okay, so now our stack is 328. So now it's 328, 2, divide. Okay, so now I want to divide by 2, 28. So that gives us 14. Put that back onto the stack. Get a plus. We've got 14 and 3 on the stack. We add them together and we result with 17.
So if there isn't operator like star or if I string? Oh, I know.
Yeah, stars or any operator you just push onto the, sorry, anything that's not our operator you push onto the stack. Yes.
So whenever there's an operator, it will only go to the previous two numbers.
Yep. It'll just grab the last two numbers in the stack. So it makes it completely unambiguous because every operation works the same way, which is that you just pop off the two things on the stack. So you pop off that one, that's B. Pop off again, that's A. Then you do A operation B and push that result onto the stack. Okay. So it's not too bad to basically figure out how to do this. In fact, I think what I'm going to do is that I'm going to make this a practice problem. I might make this one or another one a practice problem for your practice exam. So I might give it to you as a practice exam problem. So create a stack of integers. While there's where there's more stuff to read in the string, get the first token. Is it a number? If it is, put it on the stack. If there's some more stuff, get the token. Is it a number? Push it onto the stack. Is it a number? Oh no, it's an operator. Get the right operand. Get the left operand. Evaluate them. Push it onto the stack. Okay. So this algorithm is fairly straightforward. The more difficult thing, which I'll probably leave for, I was going to give you an assignment, and I was going to either give you mazes or converting from Infix to Postfix. And honestly, mazes sounded a heck of a lot more interesting than doing this. And I hope you agree. So the idea is, how can I convert basically any kind of Infix to Postfix? Now, this is sometimes given as actually a homework in like lower level programming classes. So there are things to do with that. But that's all we have for really stacks. So stacks are pretty simple, but their applications are, massive. You can do a lot with the stack. Yes?
How do you differentiate between like 2, 0, and 20?
You keep them together as tokens, so you assume that this is an array, right? If they weren't, they'd have to be separated by spaces or by commas or by something. They have to be separated by something. It's the same way that basically we can differentiate between 40 and 20 and 4020, because there has to be some way of differentiating between them, right? There has to be some way baked in, be it spaces or commas or what have you, right? But that's an excellent question, and the answer is whatever we decide is the way to differentiate them. All right. So stacks are going to be on the exam. We're going to continue going on chapter 4. There's going to be like one question, like one or two questions, one probably conceptual, one based on coding. Yes?
When's the actual date of the exam?
So not this week, but your next lab. Not this lab, but the lab afterwards. So let's go ahead and find out what the actual date that is. 22nd or 23rd, depending on what day you take it. What day. So what are you allowed to bring? You are allowed to bring a cheat sheet, front and back. What size is the cheat sheet? Great question. A4 or letter sized. Either of those. So that means you're basically standard print, basically your standard size paper, standard, and A4 is standard for non-US. And letter is standard for US. So 8.5 by 11. Right. So you can bring less if you want, but you can bring front and back. Otherwise, you're allowed to put whatever you want on it. You're allowed to put, you're allowed to, it doesn't have to be handwritten, but I suggest it because it's easier to remember that way. Like, so if you want to print it out, everything in like microflash on that paper and bring in a magnifying glass, you're more than welcome to. But you're going to spend more time seeking for the answers than actually, writing them. The other thing to keep in mind is, it's the act of preparing it. The act of writing it down will help you remember. So you actually won't have to look up nearly as much stuff, right? So I'm in the process of rewriting your practice exam and your actual exam. So let's see how that's going. Teaching, destruct. So exam 1 practice, right? So basically I'm just writing the questions like write a sequence commands that would remove the tail of a doubly linked list. Write a method that takes in 2 sorted linked lists and merges them into 1 sorted linked list and returns them. So that one's one that I really liked, but I think it was too difficult to put on the actual exam. So I throw it on the practice exam instead. write a method that reverses a doubly linked linked list, right? It's actually pretty. It's non-trivial with a singly linked list, right? And I mentioned that basically that I'll tell you in the problem that basically if it's an instance method inside linked list, that if it's inside linked list, then you get to use the nodes. If it's not inside the linked list method, right, you don't get to use the nodes because so all this stuff will probably be inside the linked list. So that's one thing to remember. Like if you're solving problems up here where I'm saying just take in any straight old list, right, and get the minimum maximum values of them and return them, right? Given a list of integers, it doesn't say it's a linked list, so you don't know if it's going to have a head or a tail, right? All you can use are the list methods like get and set, right? Okay, and then another thing to note is that pretty much for every coding point a problem, there's a 2-pointer on the bottom that says what's the time complexity of the algorithm. In other words, what's your big O notation for what you just wrote, and we are able to figure that out. So it may not be, you don't have to write an optimal solution. You just have to give me what you wrote, right? Okay, so that's what your exam or practice exam will look like, right? Questions like this, follow the links. I'm gonna replace this question with something a bit more exciting. You know, do some stuff that's like from the second lab and from your timed lab. Then write some linked list problems. You know, problems that show that you know how to manipulate linked lists. So, and basically it will be a good reflection of what's on the actual exam. Okay. Hopefully that makes you a little less stressed about it. So now let's go ahead and move on to chapter 4 because why not? You know, okay. So I mean, you guys are paying for data structures. You might as well get data structures. All right. So chapter 4 is just as easy as chapter 3 was. It's about queues. Okay. Queues are very easy to explain. You know what a queue is. Ta-da! You're done. Okay. Queue is a line. Right? Right? Queue, you hear the term queue in the Commonwealth nations a lot instead of line, but a line is a queue. Okay? They are first in, first out data structures. In other words, I'm the first person in the line, so I'm the first person to go on the ride. Right? That makes sense? Makes sense to everybody that if I'm the first person in the line, I'm the first person to get on the right. So it's useful now. Believe it or not, just because it has a simpler, easy way to simulate, because it's like easy to understand what it simulates, and because it simulates something so directly, its applications are a bit fewer than stacks, but they're no less important. So it has a couple of weird methods. I like the terms NQ and DQ, right? NQ to get into the queue, DQ to get into the queue. But Java uses the terms offer and add and remove and pull. Peek, and I don't know why they use two different things, but furthermore, you don't actually ever use a queue in Java. Like stack is a class that you can implement. Queue is an interface. Okay, sorry, stack is a class you can initialize. Queue is a interface. So most of the time when you do a queue, you're probably going to say like something like QL is equal to new linked list or something like that, or QQ is equal to new linked list, or QQ is equal to new array list. So let's go ahead and see what we've got. So queue, like a stack, is a widely used data structure. It is first in, first out, as opposed to last in, first out. So last thing that goes into the stack is the first thing out, right? The top of the stack is the first thing to come out. Queues have a front and back, right? So you in-queue in the back, and you slowly and the front of the line is slowly removed. And so eventually you start at the back, but eventually you become the front of the line, and some other poor and unfortunate soul is now the back of the line, waiting to get to that ride on Disney, right? Those queues can stretch for hours on end, right? So, right, the next person in line is it's whoever's waited the longest, right? That's typically the way we consider the most fairest. If you're willing to stand in the queue for that long, for the longest, you get to be the first in line for the queue. And you show how willing you are by staying in the queue. So this is a typical queue you have seen before, the print queue, right? Operating systems use the queue to keep track of basically some kind of scarce resource. So basically, whose turn is it to get CPU power, right? Whose turn is it to get more power? Whose turn is it to get to access this resource, the keyboard, right? Whose turn is it to access the printer, right? We're going to be waiting here a while because we're printing 52 pages, 46 pages, and 54 pages, right? So, so basically, the idea here is that what they're saying is that basically because printing does not take isn't an instantaneous process. People have to wait as their documents queue up at a printer, right? There's always that guy printing out the 30-page essay, right, that you have to wait for, right? Now, it does not make sense to use a stack for a printer queue, right? Because if it was a stack, then think about it. I could cut in front of you, right? But not only that, we're now in a game theory's arms race. Because now, okay, I printed page A, you're printing page B, you cut in front of me, so my solution is, if I want my stuff printed as soon as possible, I just hit the print command again, and now because it's a stack, I'm on top again. And so you simply do that, and it just simply repeats until basically one of us gets tired, right? And now there's probably like a million pages printing because we've created a bunch of duplicate stuff. So we definitely don't want to stack because humans are jerks. We want a queue. Right? So by the way, if you're the first person to go, basically that would mean you're the last person. So long as there's people who want to print, you might be waiting a while. All right. Also, we can use a queue for traversing a graph. We've learned kind of through passing what depth first search is, which is basically that we simply go down a corridor then back up. Okay. Queues, so if you're doing exploration and you're going down a corridor and then backing up as necessary, that's called depth first search. And you're doing, and you typically use a stack for that. You can use a queue to do exploration, but instead what you're going to be doing is you're using a breadth first search if you do that. Basically, you're going to be going basically one step down one corridor, then one step down the other corridor, then one step down the other, then two steps down that one. And then two steps, and then two steps, and then three. Basically, you're exploring all the branches at the same time in the hopes that basically that now this one requires a bit of different mental modeling but for the computer, it's no problem at all. Okay, we're going to learn way more about that in chapter 10, or as we go, or if we decide to, up this problem a bit. But here's our methods. Offer an item, which puts it into the queue. Okay. True if you can put it into the queue. False if you can't. Remove an item or pull. So let's go ahead and skip remove because it's a duplicate. Offer an item to enqueue something, and pull an item to dequeue something. So you pull it to remove the front of the queue. Offer adds the item at the end of the queue. Pull removes the front item of the queue. Does that make sense? So again, it's just really 4 operations. Offer to add to the end, pull to remove from the front, peek to get the front item, just like a stack would, and empty to check whether or not the queue is empty. Right? The only thing that's different is instead of push and pop, we have offer and pull. And if you think those are weird, you're more than welcome to use enqueue and dequeue. I will understand what you mean. Okay. So linked list is kind of perfect for doing this, by the way. So most of the time, we can implement the queue interface by using a linked list. So linked list, so queue string of names is equal to a new linked list. And this has been true since Java 5, which was when basically all this major stuff like generics were introduced. So we can create a new queue reference called names, and it stores a bunch of string objects. But you're using a linked list, right? Because a queue, remember, is just a dumb list, right? It's a list where you can't manipulate the middle of it. Just like a stack is kind of a dumb list. It's something you can't manipulate the middle of it. We just happen to be a lot more forgiving of stacks because there's a lot more cool applications of them. So, right, the idea here is, let's see. So we can implement a queue interface using a linked list. right? Because we'll be able to do all operations in constant time. So you add something into the front of the queue, and you can remove it from the back of the queue. We can also use something called a circular array, where it's actually a bit more interesting. Right? The idea here with a double E or single linked list is that basically you waste that space, remember, with the pointers. So why don't we try not using that space? So instead, let's try an array. Inserting into the rear of array, right, that's constant time. Removing from the rear of array is constant time. But if we're pushing stuff onto the front of the, but if we're removing from the front, we have to shift stuff over, right? And if we're adding from the front, we have to shift stuff over. So instead, what we're going to use is something called a circular array if we're going to do an array-based queue. Okay? And the idea here is that when we remove something, when we add, we keep track of basically what index is the front and what index is the rear of the queue. Okay? And then when we add something to the front, we just simply add it at that location front. Sorry, but of course you never add to the front of the queue. You always add to the rear, right? So we would add the ampersand, then the star, then the period, then the slash, then the dash. But when we remove it, we remove the front and we just simply make the next index the front. So how does this work in practice that we can wrap it around? Well, fortunately, we have the miracle of modular arithmetic. Okay, so array queue is equal to new array queue, which is what we're using. Okay, it has a capacity just like an array list would have it. So this is like an array queue, like an array list is a list, right? Its capacity is equal to the initial capacity. We'll say it's 5, and it has its own array, right? Just like we would with an array list. Okay, so this is no different than an array list. The idea here, however, is that we have a variable called front, which we start at index 0, and a rear index, which is the capacity minus 1, right? The capacity, remember, is not the size; it's what the size can go up to, right? And the capacity, so the size of this can go up to 5, so the capacity is 5. So the rear is capacity minus 1. Okay, size is equal to 0, right? Because there's nothing in the queue. So now, how does this work? So now we offer something in the queue. We want to add it to the queue. So we add it at index size. Okay. First off, if the size is equal to the capacity, we're going to reallocate, right? If we can't have any more space, we're going to copy over stuff, right? Otherwise, we can fit it, so we'll increase the size by 1 because we're adding something to it. And what index? We're going to say that the index is, sorry, that the rear is rear plus 1 plus the capacity. Sorry, mod the capacity. So in other words, we increment the rear by 1, and then store the item in there. What was rear set to initially? It was set to capacity minus 1. So it was set to 4. Okay, the rear was set to 4. So 4 plus 1 is equal to 5. Modded by the capacity, which is 5. So 5 mod 5 gives us 0. So now the rear is 0. So now we insert that item into the rear and return true. Now offer plus. Is the size equal to the capacity? 1 is not equal to 5. So we're going to increment size, increment a rear by 1, and put the data in the appropriate location now at the back of the list, at the back of the queue. So we just do that for a slash as well, right? I can just speed through this. Everybody's got this for right now. Okay. Now we're going to offer A. Okay. So we've just simply offered anything. We're full now. Okay. We don't need to regrow yet because we could always be pulling. We don't have to regrow until we don't have enough space to hold the next item we're adding. So now pull. That means we remove the front of the list. The front of the queue is a star. So pull works like this. If the size is 0, in other words, if there's nothing in there, return null. Otherwise, grab what's at the front to return it, and then move the front up by an index. Front is equal to front plus 1 mod capacity. Okay? Front is equal to front plus 1 mod capacity. So front will become index 1. Decrement the size by 1 because we now have 1 less item in there. And return the star. Now notice that the star is still in there. We're just ignoring the fact that it exists. So now we do a pull again. size is not equal to 0, return what's at the front, move up the front. So now the queue is /*a. So again, now here, what if we offer an item B? Okay, we've got our front at index 2, our rear is in index 4. Offer the item. Is 3 equal to 5? No, it's not, so we don't have to reallocate. Increment the size by 1 because we're adding a new item. Rear is equal to rear plus 1, so rear is equal to 4 plus 1, 5, mod 5, so it's equal to 0. So now we wrap around there and insert the item at that index. So now our queue is /*AB. That makes sense to everybody? So we're basically reusing the same space over and over again. So here we inserted a new item. So now it's /*ABC. So it just wrapped around on itself. And we can do that with the modular operator because this is the maximum. This ensures that we never get an index out of bounds exception. So now if we try to add a new item onto this, what happens when we need to reallocate? What we'll do is that we'll create a new list twice the size, new array twice the size, and then we'll start from the front and add one item, each item over. Right? And notice how it uses the modulo operation to make sure that it can wrap around properly. Right? The idea here is that we start at I is equal to 0, so we start at the front and keep adding that item, the appropriate offset. So now we reset the front and we reset the rear for our new list, and then we just simply continue with our algorithm. We copy. That makes sense to everybody? And so we now have as much space as we need. So circular arrays, circular buffers, they're really useful tools, especially if you need to be space efficient. And I personally think it was a really cool thing to have. Basically, you can implement it using an array, or you can use a doubly or singly linked list. But with the all the operations are constant time, regardless of whatever one you use, right? Except for the reallocation, which says that although the array reallocating an array is O of n, it is amortized. I think that means it is amortized over n items. That means that basically that we can kind of spread out that average, on average, right, whenever we add an item. The vast majority of the time, we don't have to reallocate. So we can kind of ignore the cost or spread the cost over a lot of operations. So the cost per item is actually close to constant. So we can simulate. So what can we use this for besides a line? Well, the other thing you can simulate this for is that the line on a computer often goes by another name. It's called a buffer. And if you do a buffer, what that does is that it basically just holds item until you can get to it. So in other words, when you're streaming data, when you're sending something to your, suppose you have a slow internet connection, right? And you're trying to upload a file. Well, what you're doing is that you're holding all those bits in a buffer and sending them out one at a time so that they can get to their destination basically as fast as the connection you have allows. Let's see, how much time do we have left? Rather than writing a queue, let's go ahead and go back here to give you an example of how to use this algorithm. So my solve maze algorithm uses a stack. Okay, let's go ahead and solve the maze instead of using a stack, using a queue. Maybe I'm giving you too much there. So if I am, we'll see. I'll adjust the difficulty, or I'll adjust what your responsibilities for this problem are. But let's go ahead and solve maze using a queue. Okay? And this will solve it in a breadth first search manner. Okay? Yeah, I'm kind of doing the assignment for you here, but I'll start it out with you. I'll give you a good idea of how it would start if we were doing a breadth first search. A queue of cells, queue is equal to a new linked list of cells, right? Because the idea here is that a queue, you can only implement that using a queue is an interface, so we can't create a new queue. So instead, we're going to import our linked list. Okay, I'm going to go ahead and start by marking my, let's see. Let's go ahead and see what I want the start of the maze to be. I want the start of the maze to be, let's go with cell start is equal to maze 0, 0. Now I need a way to show that this, right, the 0, 0 location of the maze. Like the maze is a grid, okay? And 0, 0 refers to the top left corner, right? Because remember, with one thing you may have not learned with graphics, but you might have picked up with the way we show arrays and two-dimensional arrays, is that, right, in most, a scam call right now. Most ways most coordinate planes, right, this is X and this is Y, right? But most of the time we're dealing with rows and columns. As a result, we don't work with the quadrant, with that quadrant. We work with this quadrant, where this is Y and this is X, right? So this is, so basically we're going down as opposed to up with our Y dimension, okay? So 0, 0 is the top left corner. It's the way the graphics work on your computer when we're referring to individual pixels. So cell start. So let's go ahead and make our starting cell a bit better. Set background to color, and to set a color, you do color dot and then whatever the color you want it to be. You can define other colors by like creating a some RGB values like this, like I think new color 100, 200, 0. Like that, I think that would create, yep, that creates a new color. We'll see what color that comes up as. But most of the time, you want to use the built-in colors. Okay, and then we want our finish. And a lot of this will apply for the stack. Finish of the maze, that's going to be at the bottom right corner, or wherever I want to put it. So rows -1, calls -1. And we'll go ahead and set its background equal to red, because I'm using red as my ending color. Start dot set background color dot red. Okay. Oh, yep, finish. So if we run this algorithm, what we have right now, solve maze queue, right? What's nice about this is that you can pretty much see your results as you're working just by hitting the run button. Which is that we got a maze now, and then we've got, oh, it was a kind of green up there, and then red. Let's go ahead and make this a smaller maze, right? Something a bit easier to see. 10 by 10, perhaps. Okay. And then let's go with, let's go ahead and just add a, and if we change this over here again, it changes it to a different RGB color. Or I thought it would. Let's go with color, oh, right, because the green is 100, 100, 100, this should be some kind of gray. Right? Okay, so now we've got our, we've got this set up. We've got a finish cell, we've got a start cell. And so the idea here is that basically if we want to start exploring, we do queue.offer, right? Our starting location to it. Okay? And our algorithm looks something like this. While I'm also going to have a Boolean done. Okay? Which basically, so while we are not done, okay, and the queue.empty is not true. Well, that's not true. So if the queue is empty, or we've hit our finishing condition, we're done, right? So why do we care about the queue being empty? Well, if the queue is empty, then we basically went to every location and we backtracked and we couldn't find an exit. So might as well leave the way we came in, right? Okay. So now what do we have to do? Well, the idea here is that without giving too much of the algorithm for solve maze away, because most of this, what I just wrote here, will work for what you have in the stack, is that basically you want to check north. You know, can I go north? Can I go south? So this is what I wrote on the board earlier. Can I go east? Can I go west? Right? Else backtrack. But with the way a queue works, you're not really ever going to backtrack, which is kind of useful. So let's go ahead and see here. So yeah, it's going to work a bit differently enough with the queue. So you're going to have to figure out how it works with the stack instead. So if you try to follow this directly when you're using the stack, you're going to have some trouble. Okay, so cell, yeah, let's go ahead and say cell current is equal to q dot peak. Sorry, pull. Yeah, it's going to be very different for the way you use for a stack, so I'm not too afraid of this, right? So basically, this is here you've got your current cell. Q dot pull. Now, if you try to use this and like do stack.pop over here, when you're actually solving your homework, you're going to be in a bad time. So don't do that here. It's very different the way we explore stuff. The idea here is that basically, okay, the queue has the next thing I want to look at, and what is the next thing I want to look at? What's the next location I want to explore? Okay. Okay. So, and the idea here for a queue is that, okay, if I'm exploring, if I'm doing this breadth first search, where I'm basically going down as far down a border, first I'm going to check, can I explore to the north? If, so let's go ahead and say if this, if current dot has a north wall, right? If that is not true, so if I don't have a north wall, and I haven't visited the thing to the north, not visited current dot row -1 because that's right north of me, and current dot col okay. So if I haven't been there yet, then I'm going to go ahead and add that to the queue. Q dot add let's see, q dot add q dot offer. Now it's actually much harder to do I'm trying to think about how to do a location. It's not going to work exactly the way I had my backtracking algorithm because breadth first search doesn't really work with a maze. But this was kind of rather than implementing it in front of you, which is honestly very boring, I was just trying to find something that I could do with this. So q dot offer, let's see, which cell am I doing? Oh, maze row -1 column, right? Let's go ahead and store that as a variable. Cell next is equal to maze, the current's row -1, and the current column I'm at. Offer the next into there, and then next dot set background. Set background is equal to let's say color dot blue. Why not? So if it's ready to be checked, then it's going to be blue, And then if I've been there and I'm done visiting there, current is equal to current dot current dot set background is equal to color dot green over here. That way, basically anything I've explored is green, anything I'm going to explore is blue. So what's nice is that I can copy paste this over here pretty quickly. Else boom, else boom, else boom. And then what I can do is that I can simply switch all these variables for basically north, south. So south is +1 over there. So I just simply changed over here +1. So what about going to the east? Well, east is in the same row, but east is one column that way, right? What about going west? Well, it's in the same row, but it's one column -1. -1, so I need to fix this over here. +1, -1, and let's go ahead and just see what happens here. Okay. And let's see, one last thing. Let's make this an else if. If current dot, so if current is equal to, so in other words, if current is the exact same object as the finish, done equals true. So we're going to stop. Let's see what happens if, and let's see if I get a null pointer exception if I run this. Oh, I don't think I managed to. Shouldn't you have looked at other locations too? Let's see. So this is part of the problem with the fast finding algorithm. So it started going south, 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 and then it went this way. And then was the queue empty? I mean, it pulls. It should have added.
Did it go all the way back to this first one?
No, I mean,
And then what's this?
well, we should be seeing blue stuff as well. So next, so we pull it, and then next.sec, we queue the offer next on each of these, right? Okay, we add it to each of these. Not visited. So it's checking if it's not visited. Did I mess up my? So east is a column +1, right? And west is column -1, right? So let's see. Did I miss? I mean, this is always the hazard of when you get excited and try coding something. I'm sorry. That. Yep. Always the hazard there. So offer the start, done is equal to false. So it had to have stopped because the queue was empty, right? So current.pull. So it adds my, if there's not a north. Okay, so here it went all the way straight down because it only knows how to go straight down. You pull, I mean, it should check, it only cares about if it's empty over here. Let's go ahead and see if we remove the is empty. It's probably going to run forever. Because it's going to be, yep, because it's going to try to pull something and it doesn't exist there. So let's go ahead. So current.pull, offer it next into the queue. So should be able to add the next thing into the queue. Oh, I know why. Because we made these else ifs, right? We can only add in one direction. So here we want a big else over here. Now, because in the stack, you want a bunch of else ifs. But here, we want a bunch of, we want all, it would only ever add south, right? So now, if we do these, right? So a lot of these, so yeah, it explored everything to get to the end right over there, but it found the end to get there, right? So it explores everything to get to the end. So let's go ahead and move that that stop location somewhere closer, maybe maybe at -5, -5. Okay, right? So we can see what happens. So it was looking, it stopped over here, right? And these were the next things to explore. So notice how it's basically exploring diagonally, right? The next location was probably to explore going this way, then this, right? So that's what the blue, so basically it was exploring in a, basically in a breadth first search manner. Whereas the algorithm I did was a depth first search, which basically went down a corridor. Here it's like trying, here you can imagine how this would be useful if you basically had multiple teams of people and you sent them down each corridor. This is what it's simulating essentially. So basically allows you to find a pretty short path. Now, can I draw the absolute path? I don't know. That seems like a good challenge later on, but this should give you a good start on how to solve it in the depth first search manner. It's not going to line up exactly. For instance, you definitely don't want a bunch of if-else. You definitely don't want a bunch of ifs. You want else-ifs for the way you're going, because you only want to select one direction to go at once when you're going in a depth first search manner. But I mean, we'll see. This is an experiment. If it's too tough, I'll give you guys a lot more pointers. So, because again, you don't have to really deal with too much of the graphical stuff other than setting backgrounds and the getting backgrounds I've already given to you. All right. So that's it for today's lecture. And that's it for cues, believe it or not. There really isn't too much to cues, right? We'll revisit them later, but once we start, I think on Wednesday, we'll start going over recursion. And then next week, you can expect your first exam, which will probably go over everything but recursion, but there's no point in me going over, I'm probably not going to have cues on the exam, because why?
For the next lab, the base lab, we can do it entirely using stacks, right? We don't need to use cues.
Right. The cues here was just as an example, and I'm going to give it to you as well.
Cool. Awesome. Thank you.
Mm-hmm.
My laptop. Is it okay to take the exam on Thursday?
What?
My laptop's on Friday.